You know, I've spent my entire career studying the universe, and I have to tell you, the more I learn about it, the more astonished I become. It's not that the wonder fades with knowledge, it's the opposite. Every new discovery, every deeper understanding reveals something so bizarre, so counterintuitive, so mind-bendingly strange that I find myself more amazed than when I started. So what I want to do today is share with you some of the most extraordinary facts about the universe, facts that are not speculative, not theoretical possibilities, but actual, confirmed, observational truths about the reality we inhabit. And I mean, these aren't just interesting trivia. These are facts that should fundamentally change how you think about existence, about matter, about space and time, about what's real and what's possible. Let me start with something that seems simple, but is actually profoundly weird. You are mostly empty space. Now, you've probably heard this before, but I don't think most people really grasp what it means. When you look at your hand, it looks solid, right? It feels solid when you touch something. But that solidity is an illusion, a very convincing illusion, but an illusion nonetheless. Here's what's really going on. Your hand is made of atoms, trillions and trillions of atoms. Each atom consists of a nucleus at the center, containing protons and neutrons and electrons orbiting around that nucleus. Now, the nucleus is incredibly tiny compared to the overall size of the atom. If you imagine an atom blown up to the size of a football stadium, the nucleus would be about the size of a pea sitting at the center of the field. And the electrons, they'd be like tiny gnats buzzing around in the upper seats. Everything else, all that space between the nucleus and the electrons is empty. Nothing there, vacuum. And yet, this is what makes up solid matter. The solidity you feel when you touch something isn't atoms actually touching. It's the electromagnetic forces between the electrons in your hand and the electrons in whatever you're touching. These forces repel each other before the atoms ever get close to actually making contact. So when you're sitting in a chair right now, you're not actually touching the chair. You're hovering above it by a tiny, tiny distance, maybe a few billionths of a meter, held up by the electromagnetic repulsion between the electrons in your body and the electrons in the chair. You've never actually touched anything in your entire life. Not really. It's all just forces pushing against forces. And here's what really blows my mind about this. If you could somehow remove all the empty space from the atoms in your body, if you could pack all your protons and neutrons and electrons together with no space in between, your entire body would be smaller than a grain of sand. Actually, much smaller. You'd be about the size of a dust particle, but you'd have the same mass. That's how much of you is just nothing. Now, let me tell you something even stranger. The matter that makes up your body, those atoms, those protons and neutrons and electrons, that matter is not permanent. I don't just mean that you're constantly shedding and replacing cells, though that's true. I mean that the atoms themselves, the fundamental building blocks of your body, are almost all different atoms from the ones you had a year ago. You're constantly exchanging atoms with your environment. When you breathe, you exhale carbon dioxide molecules that your body created from carbon atoms that used to be part of you. When you eat, you take in atoms that become part of you. Water molecules flow through you, in and out. The majority of atoms in your body right now weren't there a year ago, and most of them won't be there a year from now. You're more like a pattern, a process, a wave moving through matter, rather than a fixed collection of stuff. And those atoms, where did they come from originally? Well, here's where it gets really beautiful. The hydrogen atoms in your body, the simplest atoms with just one proton and one electron, most of those were formed in the Big Bang about 13.8 billion years ago. They're primordial. They've existed since the universe was just a few minutes old. But every other atom in your body, the carbon, the oxygen, the nitrogen, the calcium, the iron, all of those were forged in the nuclear furnaces of stars. Stars are giant fusion reactors. In their cores, hydrogen fuses into helium, helium fuses into carbon and oxygen, and in the most massive stars, these elements fuse into even heavier elements like iron. And then, when those massive stars exhaust their fuel and explode as supernovae, they scatter these elements into space. Those elements drift through space as gas and dust, eventually collecting into new clouds that form new stars and planets. Our sun, our Earth, and everything on Earth, including you, formed from such a cloud about 4.6 billion years ago, which means that the atoms in your body were literally inside stars at some point. They were forged at temperatures of millions of degrees in stellar cores, then blasted into space in supernova explosions, then drifted through the cosmos for millions or billions of years before eventually ending up in the cloud that formed our solar system. Carl Sagan captured this beautifully when he said, "We are made of star stuff." But it's not just a poetic metaphor. It's literally, physically true. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it came from stars. You are, in the most direct sense, a child of the stars. The universe made you, quite literally, out of itself. Now, let me tell you about time, because time is way weirder than you think. We experience time as flowing at a constant rate, 1 second per second, always forward, never backward. But that's not how time actually works, according to physics. Einstein's theory of relativity, which has been tested and confirmed thousands of times, tells us that time is relative. It flows at different rates, depending on how fast you're moving and how deep you are in a gravitational field. This isn't just theory. It's been measured. It's real. Here's an example. GPS satellites orbit the Earth at about 12,000 miles up, moving at about 8,700 miles per hour. At that altitude and speed, time runs differently than it does on Earth's surface. Special relativity says that because the satellites are moving fast, time should run slower for them. But general relativity says that because they're higher up in Earth's gravitational field, time should run faster for them. The general relativity effect wins. Time runs about 38 microseconds faster per day on the satellites than it does on the ground. Now, 38 microseconds doesn't sound like much, but GPS needs to be incredibly precise. Light travels about 1 foot per nanosecond, so 38 microseconds means the position calculation would be off by about 7 miles per day. If we didn't account for relativity, GPS wouldn't work. Your phone's map app corrects for Einstein's equations every time you use it. But here's something even more mind-blowing. The faster you move through space, the slower you move through time. If you could travel in a spaceship at 99.9% the speed of light and came back to Earth after what felt like 1 year to you, you'd find that about 22 years had passed on Earth. Your friends and family would be 22 years older, but you'd only be 1 year older. This isn't science fiction. This is real physics. Time dilation has been confirmed in countless experiments. We've put atomic clocks on airplanes and flown them around the world, then compared them to identical clocks that stayed on the ground. The flying clocks ran slower by exactly the amount Einstein predicted. We see this with particles called muons created in Earth's upper atmosphere. They're moving so fast that time slows down for them, allowing them to reach the ground before they decay, even though they shouldn't have enough time to make the journey at normal time rates. So time is not this absolute universal thing that flows the same for everyone everywhere. It's personal. It's local. It depends on your motion and your position. Two events that are simultaneous for you might not be simultaneous for someone moving at a different speed. There's no universal now that everyone agrees on. The present moment is different for different observers. And here's something that really messes with your head. According to relativity, the past, present, and future all exist equally. They're all just different locations in space-time, like different positions in space. The block universe interpretation, as it's called, suggests that all moments in time exist simultaneously, laid out like a landscape. From this perspective, your birth and your death already exist as fixed points in space-time. You're not moving through time so much as experiencing different slices of a four-dimensional reality. Now, I know that challenges our intuitive sense of free will and the flow of time. And I want to be clear, physicists debate what this means for our experience of time and choice, but what's not debatable is that relativity fundamentally changed how we understand time. It's not what we thought it was. Let me tell you about quantum mechanics now, because if you think relativity is weird, quantum mechanics is in a whole different category of strange. At the quantum level, the level of atoms and subatomic particles, the rules are completely different from anything we experience in everyday life. Here's a fact that sounds impossible but is absolutely true. A single particle can be in multiple places at the same time. Not because we don't know where it is, that would be normal uncertainty, but because it genuinely is in multiple places simultaneously in what's called a quantum superposition. The famous double-slit experiment demonstrates this. You shoot electrons one at a time at a barrier with two slits in it, and you put a detector screen behind the barrier to see where the electrons hit. Now, if electrons were just little balls, they'd go through one slit or the other, and you'd see two bright bands on the detector screen corresponding to the two slits. But that's not what happens. Instead, you see an interference pattern, multiple bright and dark bands, just like you'd get if you sent waves through the slits. Waves can go through both slits at once and interfere with themselves on the other side, creating this pattern, which means that each electron somehow goes through both slits simultaneously. A single particle is interfering with itself. It's in two places at once. And here's the really weird part. If you try to observe which slit the electron goes through, if you put a detector at the slits to see which path it takes, the interference pattern disappears. The electron starts behaving like a particle again, going through just one slit or the other. The very act of observation changes the behavior of the system. This has been confirmed thousands of times with different particles, different experimental setups. It's not a measurement error. It's not that we're disturbing the particle when we observe it. It's that the particle genuinely exists in a superposition of states in multiple places at once until we measure it, and then it collapses into a definite state. Now, what does this mean? Honestly, nobody fully understands what it means. There are different interpretations of quantum mechanics, the Copenhagen interpretation, the many worlds interpretation, pilot wave theory, and others, and they give different answers to what's really happening. But what they all agree on is the mathematics. And the mathematics says that particles can be in superposition, that they can exist in multiple states simultaneously until measured. And it's not just position. Particles can be in superpositions of having different energies, different spins, even different ages in some sense. The quantum world is fundamentally probabilistic. Before you measure a particle's property, it doesn't have a definite value. It has a range of possible values with different probabilities. Reality at the quantum level is fuzzy, indefinite, probabilistic, in a way that has nothing to do with our ignorance and everything to do with the fundamental nature of reality. Let me tell you about quantum entanglement, because this might be the strangest phenomenon in all of physics. Einstein called it spooky action at a distance, and he thought it was so weird that it meant quantum mechanics must be incomplete. But experiments have proven that entanglement is real. Here's how it works. When two particles interact in certain ways, they can become entangled. Once entangled, they remain connected, no matter how far apart they are. If you measure a property of one particle, say its spin, you instantly know the corresponding property of the other particle, even if it's on the other side of the universe. Now, you might think, okay, so the particles have opposite spins from the moment they separate, and measuring one just reveals information that was already there. But that's not what's happening. Quantum mechanics says that neither particle has a definite spin until you measure one of them. Before measurement, both particles are in a superposition of spin up and spin down. But the moment you measure one and find its spin up, the other particle instantly becomes spin down, no matter how far away it is. This has been tested in experiments where entangled particles are separated by many kilometers, and the correlations between their measurements are stronger than any classical explanation allows. The 2022 Nobel Prize in Physics was awarded for experiments confirming this. Entanglement is real. Particles can be connected in ways that defy our classical intuitions about locality and separateness. And here's what really gets me. This isn't just true for tiny particles in laboratory experiments. In principle, any particles that interact can become entangled. You are constantly interacting with the air molecules around you, with photons from the light hitting your body, with particles in everything you touch, which means you are entangled to some degree with everything around you. You are connected to the universe in ways that go beyond the obvious physical connections. Some physicists, like Leonard Susskind and Juan Maldacena, have even proposed that quantum entanglement might be related to the geometry of space-time itself, that wormholes connecting distant points in space might be manifestations of quantum entanglement. It's called the ER equals EPR conjecture, and while it's still speculative, it suggests deep connections between quantum mechanics and gravity that we're only beginning to understand. Now, let me tell you about the universe on the largest scales, because the cosmos is even stranger than the quantum realm in many ways. Here's a mind-blowing fact. The universe is expanding, and not just expanding, accelerating in its expansion. Galaxies are moving away from each other, and the farther away they are, the faster they're receding. We discovered this expansion in the 1,920 seconds when Edwin Hubble measured the distances to galaxies and found that distant galaxies are redshifted, their light is stretched to longer, redder wavelengths because they're moving away from us. And in the 1,990 seconds, two teams of astronomers studying distant supernovae discovered that the expansion is accelerating. This discovery was so unexpected, so contrary to what physicists expected, that it won the Nobel Prize in 2011. What's causing this acceleration? We don't really know. We call it dark energy, but that's just a name for our ignorance. Dark energy appears to be a property of space itself. Every cubic meter of space has a tiny amount of energy, and as space expands, you get more space, which means more dark energy, which causes space to expand even faster. It's a runaway process, and dark energy makes up about 68% of the total energy content of the universe. That means that more than 2/3 of the universe is something we don't understand, something that doesn't interact with light or matter in any way except through gravity, something that's causing space itself to expand at an accelerating rate. But wait, it gets weirder. Another 27% of the universe is made of something called dark matter. This is different from dark energy. Dark matter does interact through gravity. We can see its effects on how galaxies rotate, how galaxy clusters move, how light bends around massive objects. But it doesn't interact with light. It's invisible, transparent. You can't see it. You can't touch it. It passes right through ordinary matter without interacting. Right now, as you're sitting there, dark matter particles are streaming through your body at incredible speeds, billions of them every second. And you don't feel anything because they barely interact with the atoms in your body. They're ghosts, essentially present but intangible. So let's add this up. 68% dark energy, 27% dark matter. That's 95% of the universe that's made of stuff we don't really understand, stuff that's fundamentally different from the atoms and molecules we're made of. Everything we can see, all the stars, all the galaxies, all the planets, all the gas and dust, Everything on Earth, including you and me, that's only about 5% of the total content of the universe. We are, quite literally, a tiny minority in a universe dominated by invisible, mysterious components. It's humbling. It's astonishing. And it means that our picture of the universe is far from complete. Now, here's something that really stretches the mind. The observable universe, that's the region of space from which light has had time to reach us over the 13.8 billion years since the Big Bang, contains about 2 trillion galaxies. That's 2 trillion galaxies. Each galaxy contains, on average, about 100 billion stars. So we're talking about something like 200 billion trillion stars in the observable universe. That's a 2 followed by 23 zeros, 200 sextillion stars. And many of those stars have planets. The Kepler Space Telescope found that, on average, every star in our galaxy has at least one planet. Which means there are at least as many planets as stars, hundreds of billions of trillions of planets in the observable universe. And here's the thing, the observable universe might not be the entire universe. It might not even be close. The observable universe is just the part we can see. Light from more distant regions hasn't had time to reach us yet. The actual universe could be much, much bigger. It could be infinite. We don't know. If the universe is infinite, then there are infinitely many stars, infinitely many planets, infinitely many galaxies. And in an infinite universe with infinite possibilities, anything that can happen does happen, somewhere. There would be infinitely many planets exactly like Earth, with infinitely many people exactly like you, living lives that are identical to yours in every detail. That sounds like wild speculation, but it's actually a consequence of our best cosmological models if the universe is truly infinite. It's called the cosmological principle combined with infinite space. If space goes on forever, and the laws of physics are the same everywhere, then every possible configuration of matter must occur somewhere, and not just once, infinitely many times. Now, I don't know if the universe is actually infinite. We might never know. But the fact that it's even a serious possibility based on our understanding of cosmology, that's incredible. Let me tell you about black holes. Because black holes are probably the most extreme objects in the universe, and they're even weirder than most people realize. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The collapse is so complete, so catastrophic, that it creates a region of space-time where gravity is so strong that nothing, not even light, can escape. That's why it's called a black hole. It's a hole in space from which no light emerges. At the center of a black hole, according to general relativity, there's a singularity, a point where the density becomes infinite, where the fabric of space-time itself breaks down, where our equations give nonsensical answers. It's a place where physics as we know it stops working. But you don't have to reach the singularity to experience the weirdness of a black hole. There's a boundary around the singularity called the event horizon. If you cross the event horizon, you can never come back. Not because it's hard to escape, but because escaping would require traveling faster than light, which is impossible. Once you're inside the event horizon, all paths lead inward to the singularity. You can no more avoid hitting the singularity than you can avoid moving forward in time. In fact, inside a black hole, the singularity isn't a place in space, it's a moment in time, your inevitable future. And here's something really strange. Time behaves differently near a black hole. If you were to watch someone fall into a black hole, you'd never see them cross the event horizon. You'd see them slow down, moving more and more slowly as they approach, their clock ticking slower and slower. They'd appear to freeze at the horizon, never quite reaching it, their image becoming dimmer and redder as time goes on. But from the perspective of the person falling in, they'd cross the horizon in finite time. They wouldn't notice anything special at the horizon itself. It's not a physical barrier, just a point of no return. They just keep falling, and eventually they'd be torn apart by tidal forces as they approach the singularity. This difference in perspective, one observer sees the person frozen at the horizon forever, the other sees them cross and reach the singularity. This isn't a contradiction. It's both true. It's a consequence of how time works differently in different reference frames near a black hole. Black holes also have this property called the no-hair theorem. No matter what falls into a black hole, stars, planets, spaceships, people, all that information is erased. From the outside, a black hole is characterized by just three numbers: its mass, its electric charge, and its angular momentum, how fast it's spinning. That's it. Everything else, what made it, what fell into it, all the details is hidden behind the event horizon, seemingly lost forever. But this creates a problem called the black hole information paradox. Quantum mechanics says that information can never be truly destroyed. But if black holes erase information, then quantum mechanics is violated. Stephen Hawking spent decades thinking about this problem. He eventually concluded that information is not destroyed, it's encoded on the event horizon in a way we're still trying to understand. This led to the holographic principle, which suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary like a hologram. This principle has become central to theoretical physics and might be telling us something profound about the nature of space and information and reality itself. Now, here's something that combines black holes with the expansion of the universe in a really mind-bending way. There's a boundary around us called the cosmological horizon, beyond which we can never receive information. Because space is expanding and that expansion is accelerating, there are galaxies that are moving away from us faster than light can travel through space. We can never see those galaxies, we can never communicate with them, we can never interact with them in any way. This cosmological horizon, like an inside-out event horizon. With a black hole event horizon, you can't get information out once you cross it. With a cosmological horizon, you can't get information in from beyond it. And as the universe continues to expand and accelerate, this horizon is getting closer. More and more galaxies are crossing our cosmological horizon every day, disappearing from our observable universe forever. In the far future, trillions of years from now, all the other galaxies will have disappeared beyond our horizon. Observers in our galaxy, if there are any, will see a dark, empty universe with just our local group of gravitationally bound galaxies. All evidence of the Big Bang, of cosmic expansion, of the larger universe will be gone. Future astronomers might have no way to discover the truth about cosmology. We live in a special time, a brief window in cosmic history when we can observe the full richness of the universe, when we can see the cosmic microwave background, when we can study distant galaxies and learn about the Big Bang. In a sense, we're lucky to exist when we do. Let me tell you about one more mind-blowing fact, and then we'll explore more in part 2. This one is about the nature of reality at the smallest scales. According to quantum field theory, which is our best description of particles and forces, what we call particles are not really particles at all. They're excitations, ripples, and underlying quantum fields that permeate all of space. There's an electron field that fills the universe, and what we call an electron is a localized vibration in that field. There's a photon field, and light is a vibration in that field. There's a Higgs field, and the Higgs boson is a vibration in that field. Every type of particle is actually a vibration in its corresponding field, and these fields are always there, even in empty space, even in the vacuum. The vacuum isn't really empty, it's seething with quantum fluctuations. Virtual particles are constantly popping into and out of existence, borrowing energy from the vacuum for brief instants before disappearing. This isn't speculation. These quantum fluctuations have measurable effects, like the Casimir effect, where metal plates placed very close together in a vacuum experience an attractive force due to the difference in quantum fluctuations between the plates and in the space around them. So reality, at its most fundamental level, is not made of little billiard balls bouncing around in empty space. It's made of fields, quantum fields, that fill all of space, and particles are just temporary, localized disturbances in those fields. It's closer to thinking of reality as a vast ocean, and particles are like waves on that ocean. The waves come and go, but the ocean is always there. This completely changes how we think about what's real, what's fundamental, what actually exists, and it raises deep questions. What are these fields? Where do they come from? Why do they have the properties they have? We don't have complete answers yet. We're still working on it. But here's what I want you to take away from all of this. The universe is far stranger than it appears. The solid matter around you is mostly empty space. The atoms in your body came from stars. Time flows differently for different observers. Particles can be in multiple places at once. Most of the universe is invisible dark matter and dark energy. There are hundreds of billions of trillions of stars in the observable universe. And reality itself might be better described as quantum fields than as particles. These aren't speculations. These are facts confirmed by observations and experiments, part of our established understanding of physics. And in part 2, I'm going to tell you even more mind-blowing facts about quantum mechanics, about relativity, about cosmology, about things that will make you question everything you thought you knew about how the universe works. Because the universe doesn't care about our intuitions. It doesn't care what we think should be possible. It is what it is. And our job as scientists is to figure out what that is, no matter how strange it turns out to be. And trust me, it's far stranger than most people imagine. So we've established that reality is deeply strange at every scale, from the quantum realm, where particles exist in multiple places at once, to the cosmic scale, where most of the universe is made of invisible stuff we don't understand. Now I want to take you even deeper into the weirdness, because what I'm about to tell you will challenge your fundamental assumptions about space, time, matter, and what it means for something to exist. Let me start with something that sounds impossible. You can never actually see the present. Everything you see is in the past. Now, you might think, come on, Brian, I'm looking at my hand right now. That's the present. But it's not. Light takes time to travel from your hand to your eyes. Not much time, admittedly. Maybe a few nanoseconds, but it's still a delay. You're seeing your hand as it was a few nanoseconds ago, not as it is now. When you look at someone across the room, you're seeing them as they were a few tens of nanoseconds ago. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun, 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd keep seeing it in the sky, keep feeling its warmth, because the light and heat that left the sun 8 minutes ago would still be reaching us. The nearest star, Proxima Centauri, is 4.2 light years away. When you look at it, you're seeing it as it was 4.2 years ago. It might not even exist anymore. It could have exploded, and we wouldn't know for another 4 years. When we look at distant galaxies billions of light years away, we're seeing them as they were billions of years ago, when the universe was much younger. We're literally looking back in time. In fact, there's no such thing as a universal now that everyone agrees on. According to relativity, simultaneity is relative. Two events that are simultaneous for you might not be simultaneous for someone moving at a different velocity. Your present moment is different from someone else's present moment. The very concept of now is observer dependent. This has profound implications. It means that, in some sense, the past still exists. It has to, because different observers disagree about what constitutes now. Some events that are in your past might be in someone else's future. The block universe picture I mentioned in part 1 takes this seriously. All moments in time exist equally, and the flow of time is something that emerges from our consciousness, not something fundamental about the universe. Now let me tell you about the speed of light, because it's far more significant than just being a speed limit. The speed of light, 186,282 miles per second, or about 300,000 kilometers per second, is actually the speed of causality. It's the maximum speed at which information, at which cause and effect can propagate through the universe. But here's what's really mind-blowing. The speed of light is not just a speed limit for matter and energy. It's built into the very structure of space-time. Light doesn't travel at this speed because photons are trying really hard, and that's the fastest they can go. Light travels at this speed because that's the conversion factor between space and time in the equations of relativity. Light speed is the speed at which something with no mass must travel. It's not that photons are going fast, they're simply moving through space-time in the only way they can. And massive particles, they can never reach the speed of light because it would take infinite energy to accelerate them to that speed. As you go faster and faster, you gain relativistic mass, and it takes more and more energy to accelerate you further. At 90% the speed of light, you have more than twice your rest mass. At 99% the speed of light, you have about 7 times your rest mass. At 99.9999%, you have hundreds of times your rest mass. To actually reach light speed would require infinite energy, which is impossible. But here's something that trips people up. While nothing can move through space faster than light, space itself can expand faster than light. And it does. The expansion of the universe means that distant galaxies are moving away from us, carried by expanding space at speeds that exceed light speed. A galaxy that's about 14 billion light years away is receding from us faster than light because the space between us and that galaxy is expanding so rapidly. This doesn't violate relativity because the galaxy isn't moving through space faster than light. Space itself is expanding. It's like dots on a balloon. As you inflate the balloon, the dots move apart. Not because they're moving across the surface, but because the surface itself is stretching. In the same way, galaxies are moving apart because space between them is stretching. Now, let me tell you about something called the Planck length, because this is where things get really fundamental. The Planck length is about 10 to the minus 35 meters. That's a decimal point followed by 34 zeros and then a 1. It's incredibly tiny, about 10 to the minus 20 times smaller than a proton, which is already incredibly small. Why is the Planck length special? Because it's the scale at which quantum effects of gravity become important. At distances smaller than the Planck length, our current theories, general relativity and quantum mechanics, break down. They give nonsensical answers. We'd need a theory of quantum gravity to describe what happens at these scales, and we don't have a complete theory yet. But here's what many physicists suspect. Space and time might not be continuous below the Planck scale. They might be discrete, grainy, quantized. Space might be made up of fundamental units, like pixels on a screen, with the Planck length being roughly the size of each pixel. Time might advance in discrete ticks, with the Planck time about 10 to the minus 43 seconds being the duration of each tick. If this is true, it means that space and time are not infinitely divisible. You can't keep zooming in forever. At the Planck scale, you hit a fundamental limit, a graininess to reality. It's like how a photograph looks smooth from a distance but reveals individual pixels when you zoom in. Reality itself might have pixels. This is still speculative, but it's taken seriously by researchers working on quantum gravity. Loop quantum gravity, for instance, explicitly describes space as being made up of discrete loops at the Planck scale. String theory, while treating space differently, also suggests fundamental limits to how finely you can probe space and time. Now, let me tell you about antimatter, because this is one of the strangest predictions of physics that turned out to be absolutely true. For every type of particle, there exists an antiparticle with the same mass but opposite electric charge and other quantum properties. The antiparticle of an electron is a positron, same mass, positive charge instead of negative. The antiparticle of a proton is an antiproton, same mass, negative charge instead of positive. When a particle meets its antiparticle, they annihilate each other, converting entirely into energy, typically gamma rays. The equation is E equals mc squared, Einstein's famous formula. The mass of the particle and antiparticle is converted completely into energy. It's the most efficient energy conversion process in physics. 100% of the mass becomes energy. Antimatter isn't science fiction, it's real. We create it in particle accelerators all the time. Positron emission tomography, PET scans used in medicine rely on positrons, the anti-electrons. Naturally occurring positrons are emitted by certain radioactive isotopes. But here's the puzzle. Why is the universe made of matter rather than antimatter? The laws of physics, as we understand them, are symmetric between matter and antimatter. When the universe formed, equal amounts of matter and antimatter should have been created. And they should have annihilated each other, leaving nothing but photons, a universe of pure light with no matter at all. But that's not what happened. Somehow, there was a tiny imbalance, about one extra matter particle for every billion matter-antimatter pairs. Those billion pairs annihilated into photons, which we see today as the cosmic microwave background. And that one extra matter particle that became everything, every atom and every star, planet, and living being came from that tiny excess of matter over antimatter. We don't know why there was this asymmetry. It's one of the big unsolved problems in physics. There are theories involving processes in the early universe that violated the symmetry between matter and antimatter, but we haven't confirmed them yet. The fact that we exist at all is due to some subtle asymmetry in the laws of physics that we don't fully understand. Let me tell you about something called the Pauli exclusion principle, because this principle is literally what prevents you from falling through the floor. Wolfgang Pauli discovered that certain particles, fermions, which include electrons, protons, and neutrons, obey a rule. No two identical fermions can occupy the same quantum state at the same time. What does this mean practically? It means that electrons in an atom have to occupy different energy levels. They can't all crowd into the lowest energy state. This is why atoms have their structure, why chemistry works the way it does, why the periodic table exists. Electrons fill up energy levels one by one, and the arrangement of electrons in different levels determines how atoms bond with each other. But more fundamentally, the exclusion principle is what gives matter its solidity. When you try to push two atoms together, you're trying to squeeze their electron clouds into the same space. The exclusion principle says they can't occupy the same quantum state, so they resist being squeezed together. This resistance is what we experience as solidity, as the feeling that matter is impenetrable. Without the Pauli exclusion principle, all the electrons in your body would collapse into the lowest energy state, and you'd collapse into an incredibly dense point. Matter as we know it couldn't exist. The fact that you have structure, that you're not a collapsed blob, is entirely due to this quantum mechanical principle. And here's something that blows my mind. This principle is absolutely strict. It's not that it's hard to put two electrons in the same state, it's impossible. The wave function of a system of identical fermions is antisymmetric, which mathematically forbids two of them from being in the same state. It's a deep principle of quantum mechanics with no classical analog. Now, let me tell you about energy and mass, because they're far more interchangeable than most people realize. Einstein's E equals mc squared tells us that energy and mass are really two forms of the same thing. You can convert mass into energy, as happens in nuclear reactions and matter-antimatter annihilation, but you can also convert energy into mass. In particle accelerators, we do this routinely. We smash particles together at high energy, and that kinetic energy converts into new particles. The Large Hadron Collider, for instance, created Higgs bosons by colliding protons at enormous energy. The Higgs bosons didn't come from the protons, they came from the kinetic energy of the collision. Energy literally transformed into matter. And here's something even stranger. Most of your mass doesn't come from the Higgs field giving mass to your particles, as you might have heard. About 99% of your mass comes from the binding energy of quarks inside protons and neutrons. Quarks are held together by gluons, which mediate the strong nuclear force. The energy of the gluon fields binding the quarks together, that energy has mass through E equals mc squared. So you're mostly made of binding energy, not stuff. In fact, the more we learn about physics, the more we realize that what we call stuff, solid, substantial matter, is really just energy in various forms. Particles are excitations of quantum fields. The mass of particles comes mostly from field energies. Solid matter is mostly empty space held together by electromagnetic forces. At the deepest level, there might not be stuff at all, just patterns of energy and information. Let me tell you about something called the uncertainty principle, because it's one of the most fundamental features of quantum mechanics and one of the most misunderstood. Werner Heisenberg discovered that there are pairs of properties like position and momentum, or energy and time, that you cannot simultaneously measure with arbitrary precision. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't due to imperfect measuring instruments. It's not that we're disturbing the particle when we measure it, though that's part of it. It's deeper than that. The particle genuinely doesn't have a precise position and momentum simultaneously. These properties are fundamentally uncertain at the quantum level. This has profound consequences. One consequence is quantum tunneling. If a particle doesn't have a precisely defined position, then there's a small probability it can be found on the other side of a barrier, even if it doesn't have enough energy to classically go over the barrier. It's as if the particle tunnels through the barrier. This isn't just theoretical. Quantum tunneling is how the sun works. The protons in the sun's core don't have enough energy to overcome the electromagnetic repulsion and get close enough to fuse, not classically anyway. But quantum mechanically, they can tunnel through the energy barrier and fusion happens without quantum tunneling. The sun wouldn't shine and we wouldn't be here. Quantum tunneling also allows radioactive decay. A nucleus can be stable for a long time, but eventually a particle tunnels out and the nucleus decays. You can't predict when a particular nucleus will decay. You can only calculate the probability. It's fundamentally random, genuinely indeterministic. And here's something really weird. There's an energy-time uncertainty relation too. If you measure energy over a short period of time, there's uncertainty in the energy. This allows for quantum fluctuations where particle-antiparticle pairs can pop into existence out of the vacuum as long as they annihilate quickly enough that the violation of energy conservation is within the bounds of the uncertainty principle. This is happening all the time, everywhere in the vacuum around you. Virtual particles are constantly appearing and disappearing. These aren't real particles in the usual sense. You can't directly observe them, but they have real effects. They contribute to the mass of the electron through something called self-energy. They affect how charged particles interact through vacuum polarization. the vacuum is not empty. It's a seething foam of quantum activity. Now let me tell you about the cosmological constant problem, because it's one of the biggest mysteries in physics, and it shows just how much we don't understand. When Einstein first developed general relativity, he added a term to his equations called the cosmological constant. It represents a constant energy density filling space homogeneously. Einstein later called it his biggest blunder, but it turns out it might be real, it might be what we now call dark energy. Here's the problem. When you try to calculate what the cosmological constant should be using quantum field theory, you get an answer that's wrong by a factor of 10 to the 120. That's not a typo. The theoretical prediction is 10 followed by 120 zeros times larger than the observed value. It's the worst prediction in the history of physics. Why is the calculation so wrong? We don't know. There might be some mechanism that cancels out most of the vacuum energy, leaving only the tiny amount we observe, but we don't know what that mechanism is. It's one of the deepest unsolved problems in theoretical physics. It suggests that we're missing something fundamental about how quantum mechanics and gravity fit together. The small but non-zero value we do observe is also puzzling. If the cosmological constant were much larger, the universe would have expanded so rapidly that galaxies and stars could never have formed. If it were much smaller or negative, the universe might have recollapsed before complex structures could form. We seem to live in a universe with a cosmological constant that's just right for life. This is sometimes used as an argument for the multiverse. Maybe all values occur in different universes, and we're in one with a value that allows for observers. Let me tell you about the arrow of time, because it's one of the strangest features of our universe. The laws of physics at the fundamental level are time reversible. If you watch a movie of particles colliding and reverse it, you can't tell which direction is forward in time. The laws work the same both ways, but the universe clearly has an arrow of time. We remember the past, not the future. Eggs break but don't spontaneously reassemble. Coffee cools down but doesn't spontaneously heat up. Entropy increases. There's a clear direction to time in our experience and in thermodynamics. Where does this arrow come from? The answer, as I mentioned in part one, is that the universe started in a very low entropy state. The Big Bang was highly ordered, uniform, smooth. And the second law of thermodynamics says entropy increases. So as time progresses, the universe moves from low entropy to high entropy, and that increase defines the arrow of time. But here's what's weird. Why was the entropy so low at the beginning? This is not explained by current physics. It's just a fact about the initial conditions of the universe. A generic state for the universe would be high entropy, a uniform soup of particles with no structure. The Big Bang was incredibly special, incredibly unlikely, and we don't know why. Some physicists think this is where the multiverse comes in. Maybe most universes don't have a low entropy beginning. Maybe most universes are boring, high entropy, with no structure and no observers. We find ourselves in a special low entropy universe because only such universes can have complexity, structure, and life. It's anthropic selection again. But there's another puzzle. If entropy always increases, then if we run time backward from now, entropy should decrease, right? But that means the Big Bang had even lower entropy. And as we go further back, entropy should get lower and lower. But there's a limit. Entropy can't go below zero. So what happens at the Big Bang? Do the laws of thermodynamics break down? Do we need new physics? These are open questions. The arrow of time is intimately connected to the nature of the Big Bang, to the initial conditions of the universe, to why there's something rather than nothing. And we don't have complete answers yet. Let me tell you about neutron stars, because they're some of the most extreme objects in the universe after black holes. When a massive star runs out of fuel and explodes as a supernova, the core can collapse into a neutron star, a ball of neutrons held up by the Pauli exclusion principle. Neutron stars are incredibly dense. A neutron star has about 1.4 times the mass of the Sun compressed into a sphere only about 20 kilometers in diameter. That's roughly the size of Manhattan, but with more mass than the entire Sunday. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. If you dropped it, it would fall straight through the Earth's crust and keep going until it reached the center. The gravity on the surface of a neutron star is about 2 billion times stronger than Earth's gravity. If you were standing on a neutron star, which you couldn't because you'd be crushed instantly, you'd weigh billions of times more than you do on Earth. Light is significantly redshifted, escaping from the surface because of the intense gravity. Neutron stars also spin incredibly fast. Some neutron stars, called pulsars, emit beams of radiation that sweep across space like lighthouse beams. We detect these as pulses, hence the name. Some pulsars spin hundreds of times per second. Imagine something with more mass than the Sun, the size of a city, spinning 700 times per second. The equator of such a neutron star is moving at a significant fraction of the speed of light. The magnetic fields of neutron stars are also extraordinary, trillions of times stronger than Earth's magnetic field. In the most extreme cases, called magnetars, the magnetic field is so strong that it would be lethal from thousands of kilometers away. It would distort the electron clouds of atoms in your body, disrupting the chemistry of life. You'd be dead before you even got close. Inside a neutron star, matter exists in states that we can't reproduce in laboratories. The density is so high, the pressure so extreme, that we're not entirely sure what happens. At the very center, protons and electrons might be squeezed together into neutrons, or matter might exist in some even more exotic state, quark matter, where the quarks are no longer confined inside individual neutrons, but flow freely in a quark soup. We've learned a lot about neutron stars recently from gravitational wave observations. In 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars spiraling into each other and merging. This event was also observed in electromagnetic waves, gamma rays, X-rays, optical light, radio waves. It was the first time we observed the same event in both gravitational waves and light. That observation confirmed that neutron star mergers are where many of the heavy elements in the universe are made. The extreme temperatures and densities in the merger create elements like gold, platinum, uranium. The gold in your jewelry, the iodine in your body, these elements were likely forged in neutron star collisions billions of years ago. Now let me tell you about the cosmic microwave background in more detail, because it's one of the most important observations in all of cosmology. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this, the universe was a plasma, a hot soup of charged particles and photons. Photons couldn't travel far because they kept scattering off the charged particles. The universe was opaque. But when atoms formed, photons could suddenly travel freely. The universe became transparent. And the light that was released at that moment has been traveling through space ever since. We see it today as the cosmic microwave background, a faint glow of microwave radiation coming from every direction in the sky. The CMB is the oldest light in the universe. It's a baby picture of the cosmos, showing us what the universe looked like 380,000 years after the Big Bang, long before the first stars or galaxies formed. And it's remarkably uniform. In every direction, the temperature is almost exactly the same, 2.725 Kelvin, just a few degrees above absolute zero. But not perfectly uniform. There are tiny variations, about 1 part in 100,000. These tiny ripples in temperature correspond to tiny variations in density in the early universe. And those density variations, amplified by gravity over billions of years, grew into the galaxies and galaxy clusters we see today. By studying the pattern of these ripples, we can learn incredible things about the universe. We can measure the total density of matter and energy. We can determine the age of the universe. We can test whether space is flat, positively curved, or negatively curved. We can look for evidence of inflation. The CMB is a treasure trove of information about cosmology. And here's something amazing. The light in the CMB has been traveling for 13.8 billion years. But because space has been expanding while the light travels, the region that emitted the light we're seeing now is actually about 46 billion light years away. That's our cosmic horizon, the edge of the observable universe. We can't see beyond that because light from more distant regions hasn't had time to reach us yet. But the universe doesn't end at our cosmic horizon. It keeps going. How far? We don't know. It could be much bigger than the observable universe. It could be infinite. We might never know. Let me tell you about something called the holographic principle, because it suggests something deeply strange about the nature of reality. The holographic principle emerged from studying black holes, but it might apply to the universe as a whole. Here's the basic idea. All the information contained in a three-dimensional region of space can be encoded on its two-dimensional boundary. Just like a hologram encodes three-dimensional information on a two-dimensional surface. This sounds abstract, but it has precise mathematical formulation. For black holes, this principle says that all the information about what fell into the black hole is encoded on the event horizon. The event horizon is a two-dimensional surface, but it contains all the information about the three-dimensional interior. In some sense, the interior of a black hole might be a holographic projection of information stored on its surface. String theory, through something called the ADS-CFT correspondence discovered by Juan Maldacena, provides a concrete realization of holography. In certain space-times, a gravitational theory in a region of space is exactly equivalent to a quantum field theory on the boundary of that region. They're underseeing not just similar, they're mathematically equivalent, different descriptions of the same physics. This suggests that what we think of as three-dimensional space might actually be a holographic projection of information encoded on a distant two-dimensional surface. Space might be an illusion, in a sense. The fundamental description of reality might be in terms of information on a boundary, and the three-dimensional space we experience is a derived, emergent concept. If this is true, and many physicists think it is, then it has profound implications. Space, dimensionality, even gravity might not be fundamental features of reality. They might emerge from something more basic, quantum information, entanglement, mathematics. We might live in a holographic universe. Now let me tell you about the quantum measurement problem, because it gets at one of the deepest mysteries in physics. Quantum mechanics says that particles exist in superpositions, multiple states at once until they're measured, but what counts as a measurement? When exactly does the superposition collapse into a definite state? This is the measurement problem, and physicists have been arguing about it for nearly a century. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, says that measurement causes collapse, but it doesn't specify what constitutes a measurement. Is it interaction with a macroscopic apparatus? Is it observation by a conscious being? The Copenhagen interpretation is fuzzy on this point. The many worlds interpretation, proposed by Hugh Everett, takes a different approach. It says there's no collapse. When a quantum measurement happens, the universe splits into multiple branches, one for each possible outcome. In one branch, you measure spin up. In another branch, you measure spin down. Both outcomes happen just in different branches of reality. There's no randomness, no collapse, just an ever-branching tree of parallel universes. This sounds crazy, but it solves the measurement problem cleanly. It takes the mathematics of quantum mechanics completely seriously without adding extra assumptions about collapse. And many physicists, including some very prominent ones, think it's the correct interpretation. Then there are other interpretations. Pilot wave theory, which adds hidden variables guiding particles. Objective collapse theories, which say collapse happens spontaneously when systems reach a certain size or complexity. Cubism, which treats quantum states as representing an observer's knowledge rather than objective reality. We don't know which interpretation is correct. They all make the same predictions for experiments, so they're empirically equivalent. But they give radically different pictures of what's real, what happens during measurement, whether reality is deterministic or random, whether there are parallel universes. This is not just philosophy. It's about the nature of reality itself. And after nearly a century of quantum mechanics, we still don't have consensus on what it means. Let me tell you about the fine structure constant, because it's one of the most mysterious numbers in physics. The fine structure constant, denoted by the Greek letter alpha, is approximately 1 over 137. It's a dimensionless number, it has no units, and it characterizes the strength of the electromagnetic interaction. Why is alpha equal to 1 over 137? We don't know. It's not predicted by any theory. It's a number we measure experimentally, and it could, as far as we know, have been different. But if it were different by more than a few percent, chemistry would work differently, atoms would be unstable, stars wouldn't form, and life couldn't exist. The physicist Richard Feynman called alpha one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. He said, "You might say the hand of God wrote that number, and we don't know how he pushed his pencil." And it's not just alpha. There are about 26 fundamental constants in physics: the strength of the forces, the masses of particles, the cosmological constant, and so on. We can measure these numbers, but we can't explain them. They appear to be arbitrary, at least from the perspective of our current theories. Some physicists hope that a more fundamental theory, string theory, or something else, will explain why these constants have the values they do. Maybe there's only one mathematically consistent way to build the universe, and these constants follow from that. Or maybe there are many possible universes with different constants, and we're in one with values that allow for complexity and life. The multiverse and anthropic principle, again, we don't know. But the existence of these unexplained constants, these apparently arbitrary numbers that determine everything about how the universe works, is humbling. It reminds us that we don't have a complete understanding of why the universe is the way it is. Now let me tell you about something that combines quantum mechanics and cosmology in a fascinating way: the quantum origin of cosmic structure. The galaxies, galaxy clusters, and large-scale structure we see in the universe today, all of it came from quantum fluctuations in the early universe. During inflation, the universe was expanding so rapidly that quantum fluctuations were stretched to cosmic scales. These were fluctuations in the inflaton field, the field driving inflation. At the quantum level, fields are inherently uncertain, jittery, and when inflation stretched these quantum jiggles to enormous sizes, they became density variations, regions slightly denser than average, regions slightly less dense. After inflation ended and the universe transitioned to the hot Big Bang phase, these density variations survived. The denser regions had slightly more matter, slightly more gravity, and they began to collapse, forming the first stars, galaxies, and galaxy clusters. The less dense regions became the voids between clusters. So the large-scale structure of the universe, the distribution of galaxies across billions of light years, originated from quantum fluctuations at the Planck scale during inflation. The quantum became classical. The microscopic became cosmic. It's one of the most remarkable connections between the smallest and largest scales in physics. And we can observe this. The pattern of fluctuations is imprinted in the cosmic microwave background, and it matches the predictions of quantum mechanics and inflation. We're seeing the quantum nature of the early universe written across the sky. Let me tell you about virtual particles and the Casimir effect, because this shows that the quantum vacuum is not empty. In quantum field theory, the vacuum is the lowest energy state of all fields, but it's not a state of zero energy. Even in the vacuum, quantum fields are fluctuating. Virtual particle-antiparticle pairs are constantly popping into and out of existence. These virtual particles are not directly observable. They exist for such short times that they violate energy conservation within the bounds allowed by the uncertainty principle, but they have real, measurable effects. One such effect is the Casimir effect. If you place two uncharged metal plates very close together in a vacuum, they experience an attractive force. This force isn't electromagnetic or gravitational. It's due to quantum fluctuations of the electromagnetic field. Between the plates, only certain wavelengths of virtual photons can exist, those that fit between the plates. Outside the plates, all wavelengths can exist. So there's more quantum vacuum pressure outside than inside, and the plates are pushed together. This effect has been measured experimentally. It's small, the force between plates, a micrometer apart, is only about 1/10,000th of atmospheric pressure. But it's real. It's a direct demonstration that the vacuum is not empty, that quantum fluctuations have physical consequences. The Casimir effect also matters for nanotechnology. At very small scales, Casimir forces can cause tiny mechanical components to stick together. Engineers have to account for this when designing nanoscale devices. And there are more exotic predictions. Some physicists have proposed that the quantum vacuum might have enough energy density to act as dark energy, driving the accelerated expansion of the universe. But, as I mentioned earlier, when you calculate the vacuum energy density, you get an answer that's wildly wrong. So we don't understand the connection between vacuum energy and dark energy, if there is one. Now let me tell you about frame dragging, because it's one of the strangest predictions of general relativity. Frame dragging, also called the Lenz-Thirring effect, says that a rotating massive object literally drags space-time around with it as it spins. Imagine Earth as a ball sitting in honey. If you spin the ball, it drags the honey around with it, creating a swirling pattern. In the same way, Earth's rotation drags space-time around with it. This means that if you're in orbit around Earth, your orbital plane will slowly precess shift orientation due to this frame dragging. The effect is tiny for Earth. It causes orbital precession of only about 2 meters per year for a satellite in low Earth orbit. But it's been measured by the Gravity Probe B satellite, which used incredibly precise gyroscopes to detect the effect. The measurements matched Einstein's predictions to within the experimental error. Near more massive, rapidly spinning objects, frame dragging is much stronger. Near a spinning black hole, space-time is dragged around so violently that you can't remain stationary. You're forced to rotate with the black hole, whether you like it or not. There's a region called the ergosphere where this happens outside the event horizon. Inside the ergosphere, all paths lead around the black hole in the direction of its rotation. Frame dragging also plays a role in powering astrophysical jets. Some black holes have enormous jets of matter and energy shooting out from their poles at nearly the speed of light. These jets are thought to be powered by extracting rotational energy from the spinning black hole through frame dragging effects on the magnetic fields near the black hole. Let me tell you about the cosmological principle, because it's a fundamental assumption underlying modern cosmology, and it might be wrong. The cosmological principle says that the universe is homogeneous and isotropic on large scales. It looks the same everywhere and in all directions. This seems to be true. When we look at the cosmic microwave background, it's almost perfectly uniform. When we survey galaxies, we find that on scales larger than about 300 million light years,